The dance of the helix. Unveiling the hidden laws of fluid motion. Imagine a fluid trapped within a transparent cylinder. Instead of sitting still, this fluid is alive with motion, performing a complex choreography where every particle follows a precise, screw-like path. By watching the fluid expand, fade, and spin, we can look past abstract geometry to see the core principles of the physical universe: expansion, mass conservation, and rotation. The balanced flow. A perfect helix. At the heart of fluid kinematics is the study of how mass moves. In a baseline steady state, fluid particles act like a synchronized ensemble, swirling in circles around a central axis while being pushed steadily upward. The result is a perfect helical trajectory, much like the threads of a screw. In this scenario, the fluid is incompressible. As the particles rise and rotate, the spacing between them remains perfectly constant, meaning the fluid neither thins out nor piles up anywhere. When looking at the cylinder as a whole, a perfect equilibrium is established. The amount of fluid entering through the bottom disc is exactly equal to the amount exiting through the top cap. Because the fluid is swirling parallel to the cylinder's walls, no mass ever pushes out through the sides. Because what goes in must come out, the net flux, or total movement of mass across the entire closed surface, is exactly zero, beautifully validating the divergence theorem. When the balance breaks, sources and sinks. Shifting the focus from fixed paths to dynamic environments reveals what happens when fluid density changes. Introducing a source alters the rules of the system. Now, as the particles spiral upward, they are also pushed outward from the center, making the helix expand like a growing fountain. This change has a profound physical effect that mirrors the continuity equation. Sources. Expansion. Because fluid is being introduced or pushed out from the central axis, there is more fluid leaving the cylinder's surface than entering it. As the fluid expands into a larger volume, the particles physically thin out. Visually, they fade in intensity, representing a localized drop in density. Sinks. Compression. Reversing this effect creates a sink, where fluid is actively drawn toward the center. Here, the particles crowd tightly together and brighten, showing that the fluid is becoming more concentrated as it compresses. The spinning paddle wheel. Understanding rotation. Even when a fluid isn't expanding or thinning, it can possess a hidden internal characteristic known as vorticity, which measures localized spin rather than the overall path of the flow. The easiest way to visualize this distinction is by dropping a tiny virtual paddle wheel into the current to see how it behaves. Rigid body rotation. In a standard rotating helical flow, the fluid moves like a solid record spinning on a turntable or a carousel. If you place a paddle wheel into this stream, it will orbit the center, but it will also spin rapidly on its own axis. This indicates that the fluid has true local rotation. Individual fluid elements are actively turning as they travel. The irrotational vortex. Contrast this with an irrotational vortex, which mimics the behavior of water spinning down a bathtub drain. Here, the particles still travel in a circular path, but the fluid closer to the center moves much faster than the fluid on the outside. If you drop a paddle wheel into this drain-like flow, it will orbit the center, but it will never spin on its own axis. It maintains its exact original orientation, pointing the same way the entire time. This happens because the severe velocity difference between the inner and outer currents pushes against the paddles in a way that perfectly cancels out the rotation of the circular path. Ultimately, this progression shows that circular paths do not inherently mean a fluid is spinning, proving that local behavior and global motion are two entirely different visual realities.